In this video, we will see some problems based on work done and energy conservation. The first problem here is a multiple choice. It is asking us in which of the following situation is no work done on a book. Now for zero work done, that is no work done, we can have either the displacement equal to 0, or the object could be at rest, or the angle between the force and displacement could be 90 degrees. So that eliminates the first one, second one, and the third one. Dropping the book, here the displacement is not 0, the angle is not 90. Picking up the book, the same case. Pushing the book across the desk, again, it does not fit in any of the three conditions. But the fourth one, holding the book while walking on a flat surface. Let's just visualize it. You're holding a book and you're walking on a flat surface. There will be force of gravity on the book. The book itself is being displaced in the horizontal direction. That means the angle between the force and the displacement is 90, which means that the work done will be 0. So our answer here is D. Next problem. A 2 kg book is at rest. Mass is equal to 2 kg on a table 1.5 meter high. We've got the height of the book is 1.5 meter. It's asking us to calculate gravitational potential energy stored in the book. So this is a direct application formula. We know that GPE is equal to mgh. Mass is 2, G is 9.8 and H is 1.5. That gives us the answer as 29.4 joules. Next problem. Here the diagram shows a box being pulled along a horizontal surface with a force of 200 Newton. So F is equal to 200. Angle is 45. So theta equal to 45. Calculate the power. P is what they are asking us to calculate. And it is being pulled by a distance of 5 meters. So D is equal to 5 in 10 seconds. So time is given to us as 10 seconds. Power, the formula is work over time, and work we can calculate by the formula Ft cosine theta. We have F, we have D, we have cosine theta. We can substitute to get the answer for work done. Now this work done, we can bring it back into the power formula, substitute it there, divide it by 10, and we can get the answer as 70.7. Because we are calculating power, the unit will be watts. Let's check the next question. A 3 kg backpack, mass is 3 kg, initially at rest, so Vi is equal to 0, moves through a distance of 0.25 meter, distance is 0.25, the force is 20 Newton. What is the final speed of the backpack? Now here they are giving us force, distance and mass, and they are asking us to calculate final speed. So we need to use the work kinetic energy theorem, which says that work done is equal to the change in kinetic energy. Work done, we know it's also Fd cosine theta, so we can substitute the numbers. 20 times 0.25 cosine theta will be 1 because F and D are in the same direction. Theta is equal to 0, cosine 0 is 1. So we have to just do 20 times 0.25. We get that as 5 joules. Delta Ke is Kef minus Kei, the change in kinetic energy. Now initial velocity is 0. That means initial kinetic energy will also be 0. So Kef is half mvf square. And we know that work done and kinetic energy, delta Ke, that means change in kinetic energy, they are equal to each other. So we can equate them. Half mv square is equal to 5. Now we have to just solve it by substituting the mass, which is given to us as 3. And then we find Vf square. And do not forget to do the square root. to get Vf. That will come out as 1.8 meter per second. Let's check the next problem. A block of mass m is released from rest. From point A, it goes down a frictionless track. Determine the block's speed at points C. So this is a clear problem of energy conservation, which says that energy of block A at point A will be equal to energy of block at point C. That means energy can neither be created nor be destroyed. So at any point you check the energy, it should be equal to what it was initially. Now at point A, it can have GPE and KE. So we will just rewrite with GPE and KE as the energy of the block at point A and C. And then we will try to visualize what's happening to each of the energies. GPE is given as mgh and kinetic energy is half mv square, which we know already. Now at point A, the block was at rest. It's given to us. That means the kinetic energy at point A will be 0. So we can just remove kinetic energy from the left hand side of the equation from here, and we can just write it as GPEA equal GPE plus KE at C. Replacing each one of them with their formulas, we can see that m is appearing in every expression, so it can be cancelled out. So we get this. Now we will substitute. So G is 9.8, so 9.8 times HA, you can check in the figure, it is 5. Then G is again 9.8 and HC is 2. Plus half Vc square. We don't know what's the block speed, and that's what it's asking us to calculate. Now we use our calculator and solve the terms step by step, moving 19.6 on the left hand side, subtracting it from 49, getting Vc square as 58.8, but we don't want Vc square, we want Vc, so we need to take square root, and we get that as 7.67 meter per second. Next problem is again multiple choice. It's asking us to choose the graph which represents an elastic collision. Now for in an elastic collision, the property is that kinetic energy final should be equal to kinetic energy initial. That means there is no loss of kinetic energy. And if you look at each of the graphs, the last graph, that is graph C, we can see before and after kinetic energy remains the same. That means the final kinetic energy is equal to initial kinetic energy. That means that's our answer.